Hello, my name's Chris Kurzik, and I'm the principal engineer at Athabasca Engineering Solutions, AES for short. And what does AES do? Well, first of all, we provide third-party value evaluations. We provide training and certification. We provide equipment re-rating.
Folks. Today we're going to go through example 3.1, and it's found in an ASME publication about ASME Section 8 Division 2, and it's called ASME PTB-3, and this is the 2013 version, and we're going to be looking at some examples in part 3 of that, and this is the first example. And so in this example in particular, we're going to be looking at a circumferential seam between a shell and a head. Break down and organize the variables in example 3.1. And this is the example where we use MDMT exemption curves. So this is a ASME Section 8 Division 2 problem. It's found in part 2, which is the materials section of the code. It's going to be a post 1999, so that the rules, there was differences between the rules, prior to that period. So the allowable stresses and so on. And so, as you recall from earlier, SA 516 grade 70 is a very tough material used very quite commonly in refineries for its good impact properties. It's a normalized, medium tensile type steel, and it's the type of shell. It's a shell, cylindrical shell to a bottom head that we just saw. Nominal thickness. It's quite thick. It's 1.81. And that's part of the reasons why we're considering Division 2. And the corrosion allowance is shown there. It's a Category A welded type 1, which means it's 100% RT. And if you look at these sections over here, 422, 423, 424, they walk you through the steps of how to categorize that. So at the end of the day, there is post-weld heat treating, and it's because of code, because we're basically, we're over 1.5 inches. And so the arbitrary MDMT that our client wants us to use is -20 or -29 centigrade, and that's the target. And because of the rules of 422, 423, and 444, the RT is 100%. Therefore, we can look up in 424 the efficiency, and it's 1.0. Okay, so let's go back and derive, why do we call this Category A when we have a circumferential weld? And this is something that, I learned earlier is that for a joint between a shell on the side and a head is classified by figure 4.2.1 as a Category A connection. So, and that's the same thing with Division 1. There's a number of tables in Section 8 Division 2, and there's several of them. And the type of detail we've identified is it's a detail 1, the type 1 joint. It's on this side, of course, is the shell, on this side is the head. And we've identified that as a Category A connection. And so then we follow these design rules. Continue with this here. So this is a table 7.2, and it's for non-destructive examination. We've determined earlier that our joint category was an A, and it's a type 1 weld. So, and we've got category 1.1 material. And so basically we have to to get 1.1, 1.0 weld joint efficiency, then we need to do 100% RT. So if we do 100% RT, then we meet the criteria. Also for Section 8 Division 2, we have to do 10% magnetic particles, usually what's done. The other one is liquid penetrant inspection, mostly done for stainless steels where it's non-magnetic. So the rule is, this is note 4, says 10% if the thickness is greater than 35 millimeters, which is 1 inch and 3/8, and it's 0, you don't need to do any of that NDE if the thickness is less than 35 millimeters or 1 3/8. And with T as defined as in 7436. So there's some exemptions. So in conclusion, we are sitting at a joint efficiency of 1 because our RT is 1, and we are going to be also doing some other testing as well. Division 2 has the same kind of curves, but it's more broken out. There's a number of curves. And in this case, we're looking at a carbon steel low alloy curves, and there's an exemption to bolting, just like in Division 1. So in this material curve we're going to be using falls under 31123A. And so we would use figure 38M, which is the metric version in our example, but if it's 3, or you can use table 3.8, which is the imperial version, or you can use a tabulated form, especially if you're using spreadsheets, and you get more exact numbers. So very similar. So the parts are subject to post-weld heat treat, and these are non-welded parts. So this is where we'll start. So if we fall under that category, because they have one curve for post-weld heat treat and one for not, and then they have one for welded parts and one for not. So there's a lot more tables with Division 2. So here we go. So let's look at SA 516 grade 7, which is a normalized plate. It's going to follow under a D curve. But what you're going to see here is we follow under the D curve. It's actually lower. If you recall, you get a little bit more credit for the Division 2 for the temperature, because you're making all these, you're sharpening your pencil essentially, and you take into account the post-weld heat treat, which removes the stress from the part, and it helps to reduce the MDMT. So let's look at figure 3.8 note D. So there's some exceptions because Division 2 allows you to do more things, or to push the envelope of what your equipment can do. There's more rules and exceptions. So one of the ones is cooling rates. They have to be greater than air rates. So followed by tempering, it's permitted. Okay. The other one is there's a very strict definition of fine grain practice, and you have to go to SA 20 for that. And an interesting one that we've run across over the years is normalized rolling condition is not considered normalizing. Sometimes the vendors will say that it's hot rolled and it's been normalized in that condition. Section 8 Division 2 will not accept that for this condition, of course. There's a number of figures used to determining your governing thickness, which is step 2 basically. And in this particular example, where we have a head connecting to a shell, then basically the equation is that we would use the thickest part, right? So in this case, it would be TB, which is 46 millimeters. Moving on to step 3, the required MDMT, that is minus 29 centigrade or minus 20 Fahrenheit. And that information is provided by the client. And we organized it in that nice spreadsheet at the beginning of the chapter. Okay, let's move on to back to the exemption curve, step 4. This is where we take, now we've determined our governing thickness. Let's work on our MDMT, what it is, the adjusted MDMT. So we refer to table, in this case 3.8 or 3.15. This is what you would use for our particular alloy. And of course, we have a post-welded material and it's non-welded parts. So we are going to continue. So we have a 46 millimeter part, and we go across and we get our MDMT of minus 28. And you can see there that we chose the curve D. So let's take a look at step 5, their conclusions. We concluded that our MDMT is minus 28 degrees centigrade or minus 19. But we have a problem. It's still greater than the MDMT required. So strictly by the rules, you'd have to go ahead and look at the impact testing. But there are other ways a way around impact testing. Refer to 3.11.2.5 and 3.11.2.8. They have to do with things like the material changes, if getting in another type of material, like a forging that has a specification suited for that, or you can live within the tolerances of that allowance. Conclusions. More conclusions. Let's compare division 1 and 2. So we just finished a calculation. We determined minus 28 was our MDMT based upon how we did the analysis. If we do the same analysis as close as we can with division 1, we found out it was minus 22 degrees centigrade. So there's some real benefits, especially with the thicker the part you go, the more benefits you get on the MDMT.
I hope that you found this presentation useful and valuable to you. This was provided by Athabasca Engineering Solutions. We'd love to hear your feedback and your thoughts on further videos. And we'd love to hear from you. Maybe we can do some business. Please subscribe to our channel so you don't miss a thing. Take care for now.